Hello everyone, my name is Ricardo. I'm software manager at Espressif, and today we're going to talk about AMP. Thank you everyone for joining this presentation. Today we're going to talk a little bit about our view and our solution regarding AMP. We'll check a little bit about how we implemented and some of the backgrounds surrounding this implementation, a little bit about the configuration, some applications we imagined for this solution, and a few demonstrations on where we stand on this technology. So before we start, AMP, as we expect everyone to know, is asymmetric multiprocessing, which it happens when we have two CPU cores and two different CPU cores, or same core that work in a different way. So for example, on ESP32, we have the same core, but they behave a little bit differently on the way we understand and we have these cores. So we can consider that as asymmetric multiprocessing. So which devices we develop these solutions for? Of course, we must have multi-core. So it's for ESP32. ESP32S3, which is not developed yet, but it's on our roadmap. And we can count on future ESP32 devices that consists of multi-core. We're not talking about the low power cores here. We're just talking about the full power cores. So for example, the ESP32S2, the RISC-V contained on it, it was not addressed by this type of solution. So now diving a little bit into details, we based our solution on Zephyr. One of the reasons is because we needed to extract all the power from ESP32 devices, and we have some limitations on Zephyr regarding the networking, and also that Zephyr has a very advanced support for Open AMP, which is a nice solution to have the communication between asymmetric cores. Also, how do we bring up this application? How can this multi-core solution start? So we have one. The first option is the Zephyr app bring up. This happens when Zephyr starts the second core. And we also have when the application is started up by MCU boot directly from the bootloader. So the flow for the Zephyr bring up is that on ESP32 devices, we have the ROM bootloader. After the ROM bootloader, instead of the regular or widely known IDF boot, we use the MCU boot. MCU boot then loads Zephyr. Zephyr running on core 0, then starts up another Zephyr instance, for example, or another firmware on core 1, and it resumes its operation on core 0. When we have MCU boot to do the bring up, we have as the same, the ROM bootloader. After the ROM bootloader, we start MCU boot, and MCU boot then starts directly both the Zephyr image on core 0 and the Zephyr image on core 1. MCU boot, on all cases, is always running on core 0 before it starts the second image on core 1. So the targets that we have for the communication between the asymmetric cores is the IPM, the standard libraries on Zephyr, OpenAMP, using the Zephyr port for libmetal, or users can use all the resources they want to exchange resources, and we have then mutexes, mailboxes, and all of that. Just as a note, this is all still a work in progress from Espressif. The push requests have just recently been merged. So the configurations for these systems on which image is going to be used on each core. So the first regular use is 2 custom Zephyr images, where users can run their custom Zephyr with their custom firmware on one core, and another custom Zephyr with another custom firmware on the other core. They can or cannot have a communication between them. That's up to the application. Second, if user doesn't want the networking interfering with their own firmware, they can use Zephyr and use another core just as a network accelerator, which is kind of an on-chip offloaded networking solution. Also, users can eventually decide to run Zephyr plus image containing with a Rust image or a bare metal image. So they can have all the features from a full-fledged RTOS plus all the detailed and close to the closest they can get to the hardware with a bare metal solution. And finally, users can also have one Zephyr image and whatever factory-defined firmware they want to run, doing whatever specific task they want. It could be some sort of cryptographic library, it can be some sort of software accelerator they can have on the second core. So the second core ends up being a software-defined custom peripheral. So on these scenarios, there are several possible applications. So the first application is an offloaded solution, just like I mentioned on the configuration, where we have one Zephyr image running a custom built Zephyr, and a second image running a networking tuned specific Zephyr image. So when the system boots, in this case, it should be noted that Zephyr is going to run the second image. So Zephyr starts, then the network driver, for example, starts up the second core. On the second core runs a second Zephyr image. One question that could arise is where the second image could be located in such situation. Well, it could be on the file system, it could be bundled with the firmware built, it could be whenever location that Zephyr has access to. So which kind of applications is this scenario used for? General purpose, or in those solutions that need to reduce the number of chips. So let's say, for example, the user already have a solution that has an offloaded Wi-Fi solution plus another CPU, and then can bundle those 2 chips with and replace them with just one ESP32. The second scenario is for sensitive data computation. So users may have a connected core, a connected firmware on one of the cores, in this case on core 1, and they may have some security or sensitive data being computed on core 1. So in this case, it's favorable that they use MCU boot load. So the unsecure core won't have any kind of privilege over the secure system. And eventually they can have or may not have, depending on the application, communication between the cores. In this case, of course, more configuration besides just firing up the images have to be made to make sure that the secure software runs safely from the unsecure software or exposed software. On these scenarios, the application is point of sales, banking, imaging, and identification. Several countries have hard regulations regarding user data protection. So, for example, devices running ID, they eventually can count on this kind of application to make sure that the current and local user data don't risk being transmitted over the internet. The third scenario when user wants to isolate an IoT service provider from their custom product routines. So, for example, one user, they have some form of connectivity from a cloud provider, for example, AWS or Azure, or even Espressif Rainmaker. So they can be using the cloud provider firmware on one core and have it completely separated from their application. On this case, users may or may not use the MCU bootload, because eventually they would want to fire up the connectivity software only when needed and only when wanted. So they may have reduced the power consumption, for example, to keep one core shut off, and while still not running any kind of cloud firmware. Eventually, they can also figure that for security reasons, they just want to communicate on particular windows. So they want to shut the cloud software that come off the shelf from the cloud provider. The application for this scenario is when on typical uses for ESP32 along with an IoT cloud provider, when the user doesn't want to mix or integrate their firmware or create another build to integrate connected or the cloud provider application into their own application. Or this could be used when user wants to turn on and off for whatever reason, maybe for safety reasons, maybe for power concerns, the connected firmware. It, of course, can be used on all kinds of connected products to well-known clouds. The fourth scenario, when the cloud provider, instead of the user, wants to offer a connected off-the-shelf solution that won't require any sort of compiling and building. And eventually, in this case, users can upload their firmware through the cloud provider network. So in this case, we can have the Zephyr cloud provider to start the user custom image, where actually makes the user product. And eventually they can communicate and exchange information through OpenAMP or another protocol. This is very useful for solutions that are connected off the shelf. And users may or may not want to handle their firmware to the provider. So eventually they would like to have just receive the binaries from the cloud provider and just use the building tools so they can generate the image, and MCU boot starts up all both cores. So in this case, or even on the other case, the application is that cloud providers, they can provide a pre-built image that won't change, that will be guaranteed to be connected, provided that the user won't be changing or dealing or building the provided custom firmware, the provided firmware. They can only just start up with no, actually it can even start up with no actual application as long as it connects to the network. It downloads the user application from directly from the internet. It's also useful for OEM manufacturers. So the device ships out with zero programming, or but zero programming on the sense of a product like programming, but it can get connected to the internet and eventually download the custom firmware. So product identifies itself and downloads the proper firmware from the OEM manufacturer site or the user's website. Scenario 5, which is a scenario that was brought up due to the crisis of the semiconductor industry. With the lack of chips, several products were not manufactured properly, or they had to wait in line for complete manufacturing. And these devices, mostly when IoT and when connected, they have one critical core running critical software, or at least robust software intended to protect the user safety, the end user safety, and another core to provide the connectivity to the network. Due to the demands and lack of available devices, ESP32 can be used with an IMP solution to both have connectivity and a robust software that won't depend or won't be connected to the internet. So in this case, the user had the critical firmware on core 0 and all connected software on core 1, and critical routines or robust routines on core 0. In this scenario, users won't have the interference from all networking on the critical routines, and they can provide a safer application for their users. Critical certification always depends on the device manufacturer, and this is still a work in progress and still under study on Espressif. So we're not there yet, but at least we're building the basics and the images and all the necessary tools for this solution. Applications for this scenario: home appliances, control systems that need to be the fastest they can, industrial applications, and automotive. Okay, so this is currently our solution on AMP. It's still work in progress on Espressif. It's not more than less than 2 months, less than 1 month actually, that it was merged upstream on Zephyr. So currently, this is an intended software product. It's still in earlier than alpha stage. It's still a proof of concept to which we are discussing some applications. What comes next? If it's a software product, it's intended for people to use it. So what's come next is tooling. So we have to provide the tools for people to use it. The current state of this implementation is that there is a lot of handcrafted commands and configurations that have to be set for one to be able to build an AMP solution. It's already there, but it's far from, it's going to take a lot of time just to set up the environment, then actually building the application itself. Second to that, if it's something that people can have the tools to use, documentation, and finally, better than documentation, the examples. I would like to thank everyone for joining me on this presentation. Sylvio, my colleague, will now present some demonstrations about these solutions that we brought up and that we are working on. Thank you all for joining me, and have a nice demonstration.
Hello, my name is Sylvio. I'm a software engineer at Espressif, and today I'm gonna continue Tafas' presentation regarding AMP. And the idea here is to share with you 3 different sample codes related to AMP and IPM. So let's start. We can see here 4 folders, but it is in fact 3 samples. It's the IPM, MCU boot, and Rust. So the idea is I'm gonna show you the 3 and then flashing on the board and see the results. So the first sample is the IPM. So this is a project that's already upstreamed in Zephyr. And what we have here, it's a project within a project. So we can see here the source file of this IPM project, okay? And it's loading here. And it basically gets the IPM instance of the ESP32, right? It registers a callback, and it starts the IPM, and then it just keep like, it sends a request, and then wait for the other core to reply. So this sample code is going to run on the Pro CPU of ESP32. And there's another code in here that we call IPM ESP32 net. This one runs on the app core. And it's basically the same idea. So we have here the main call, and it just gets the IPM instance, registers the callback, enables it, and then just sends a reply to the ProCPU request. Here is the callback, so it just releases the semaphore, so the message like keep going back and forth. Okay, so first of all, I'm going to build the net sample code. I have a ESP32 board attached to my USB port. So now it's been completed, and then I just need to build the ESP32, the main project in here. So I'm running West build for the ESP32. Now that the build is completed, I'm going to flash and open the monitor to analyze the output. So I'm gonna pause the simulation. It's running. I'm gonna pause it. So what we see here is that we have the ProCPU sending a fake request and waiting response from the app CPU. Once it gets the response from the app CPU, it prints the message from the app CPU. This is a response. So this is the basic sample code that we can flash. We can use both cores independently of each other, either talking to each other or not. So we can understand the MP approach. Now that we completed this IPM sample, I can do the same thing using the MCU boot. So we need to build the MCU bootloader for the ESP32, and then we need to flash both images on each slot to each other, and then MCU boot is going to perform the proper handling to run both applications. So first thing I have to do is I'm gonna change the shell here. So currently I'm on the MCU boot upstream repository. So I'm gonna build the MCU bootloader image for ESP32. We can find this how-to on upstream's README file. And now I can flash it. So it's been flashed. So ESP32 board already has the MCU bootloader. Now I'm gonna switch to this project in here, MCU boot project. It's similar to the first one. So what we have here is the same source code. It's the same IPM sending communication to each other core. But now we're gonna flash it using the MCU boot. So first thing I have to do is I'm gonna build the ESP32 net, and I'm gonna add some overlay to enable the MCU boot. So this is building the application, that's the net one, and we're gonna flash it without starting the project. So it's going to flash it. Now we are gonna build the other project. That's the ESP32, this one here. We're gonna build it, and we're gonna use its custom overlay to enable MCU boot as well. So now that both images have been flashed, we can start it. Now they're going to flash. So I'm flashing this last image, and then we're going to open the monitor so we can take a look at the output. Okay, so I'm going to pause it. What we see here is the MCU boot banner. So it's loaded properly. And then we can see here that both images were loaded. So we have here loading image 1 and loading image 0. So we have the ProCPU running and also the app CPU running. And the behavior is the same as the first sample code. So we have the ProCPU sending a fake request, and we have the app CPU response as well. So we just, in this sample code, we just performed the same approach of the first sample, but using MCU boot. And finally, there is another approach that it's a draft, but it's something that we can allow on the AMP environment. I'm going to show you how to run Rust in the app CPU. So we're gonna run on the Pro CPU Zephyr's application and on the app CPU Rust application. So first of all, we have here the ESP hall. This is Rust repository. And I'm going to open the sample code for the Hello World. Hello World is open here. This is a basic Rust sample code. So we have the main entry in here, and you just get the instance initialization of peripherals, clocks, timer. We disable the watchdog, and then we start the timer to toggle every 1 second. So during this time, it just prints app CPU hello world from Rust. So I'm gonna build this project using the cargo build example hello world. And this is completed. Now we have some procedures to take care of. So I'm gonna use ESP2 so we can convert the ELF file generated from the build in binary file. And this is going to copy this rust.bin to the Rust folder. So I'm going to delete this, and I'm going to run ESP2 to generate this file again. Yeah, so rust.bin is here. And the next step is we still have to convert this binary file into an array file. So I'm gonna run a Python script that we can convert this binary file into this array in C. So I'm just gonna delete this one, ESP32 net firmware. And then I'm gonna run the Python script that, it's in here. The Python script to convert the rust.bin into the source file. So once we do this, it creates the array here. And Zephyr main project is going to loop every second, printing Pro CPU hello from Zephyr. And as I showed before, Rust is going to run and display hello world from Rust. So now I just have to build the project using West build for ESP32. And now I just have to flash it and open the monitor to take a look at the output. We have some garbage here. It's something that has been worked out, but we can see here, I'm gonna stop it. And we can see here, again, Pro CPU sending hello from Zephyr, and also app CPU sending hello from Rust. So in these sample codes, there's no IPM running. They are just printing some content from each core. But this it's a sample code that we can use to evaluate next steps regarding AMP support using other platforms like Rust or bare metal. And that's all I got for today. Thank you very much.